Hey everyone, and welcome back to our cosmic classroom. Today, we're diving into one of the most extreme objects in the universe, magnetars. Imagine a star so powerful its magnetic field could wipe your credit card from 100,000 miles away. These incredible celestial bodies are a type of neutron star, but with a magnetic field so intense it boggles the mind. How do such astonishing objects come into being? Join us as we unravel the explosive, mind-bending journey of how magnetars form, step by step. Before we jump into magnetars, let's establish some basics. What exactly is a star? A star is a luminous sphere of plasma held together by its own gravity, generating light and heat through nuclear fusion in its core. Think of our Sun, constantly fusing hydrogen into helium, releasing enormous energy. This outward energy perfectly balances the inward pull of gravity, defining a star's stable life. But this delicate balance doesn't last forever. Not all stars are created equal. Our Sun is a medium-sized star, but magnetars don't come from stars like ours. They originate from massive stars, at least 8 to 10 times the mass of our Sun, often much larger. These stellar behemoths burn through their nuclear fuel at an astonishing rate. Their enormous mass means their gravitational pull is much stronger, requiring far more energy from fusion. They live fast and die young, making their life cycles incredibly dramatic and fascinating. Let's briefly recap how stars power themselves. At the heart of every star, immense pressure and temperature force atomic nuclei to combine in a process called nuclear fusion. For most of a star's life, it fuses hydrogen into helium. This reaction releases a tremendous amount of energy, creating an outward pressure that counteracts the star's inward crushing gravity. It's a delicate dance, allowing stars to shine brightly for billions of years. Even for the most massive stars, fuel isn't infinite. Eventually, these giants exhaust the hydrogen in their cores. What happens? The core contracts under its own immense gravity, heating up. This allows heavier elements like helium to begin fusing into carbon and oxygen. This process continues, creating an onion-like structure of fusing shells. Each stage generates less energy, accelerating the star's demise as it struggles to maintain equilibrium. This stellar fusion can continue building heavier elements up to iron. But iron is a cosmic dead end. Fusing elements heavier than iron, unlike lighter ones, consumes energy instead of releasing it. Once the star's core is primarily iron, it can no longer generate outward pressure to counteract gravity. The star has lost its engine. This marks a critical turning point, leading to an inevitable and catastrophic collapse. Gravity finally wins, and it wins spectacularly. With no more fusion to support it, the iron core undergoes an incredibly rapid and violent collapse. Imagine something hundreds of thousands of times the mass of Earth collapsing in milliseconds. The outer layers, no longer supported, rush inward, slamming into the now incredibly dense, collapsing core. Atoms are crushed, electrons forced into protons to form neutrons, and the core shrinks to an astonishingly small size, becoming denser than anything we can imagine. This implosion is a prelude to a universal spectacle. The inward-falling material rebounds off the newly formed, superdense core. This rebound creates a powerful shockwave that blasts the star's outer layers into space at incredible speeds. This is a supernova, a cataclysmic explosion that can briefly outshine an entire galaxy. Supernovas scatter heavy elements, forged within the star and during the explosion, throughout the universe. Without them, there would be no carbon for life, no oxygen to breathe, and no iron in our blood. What's left behind after such a monumental explosion? If the original star's core had a mass between about 1.4 and 3 times that of our Sun, it won't collapse all the way into a black hole. Instead, the incredible compression forms a neutron star. This star is so dense that a single teaspoon of its material would weigh billions of tons. It's essentially a giant atomic nucleus, composed almost entirely of neutrons. These are already extreme objects, but some go even further. To truly grasp a neutron star's scale, an object with more mass than our entire Sun is packed into a sphere only about 10 to 20 kilometers, or 6 to 12 miles, in diameter. That's roughly the size of a city. They spin incredibly fast, sometimes hundreds of times per second, and have incredibly strong gravitational and magnetic fields. Remnants of stellar death, they are far from inactive, often emitting beams of radiation as cosmic lighthouses or pulsars. So, what makes a magnetar different from a regular neutron star? Both are incredibly dense remnants, but magnetars possess an extraordinarily powerful magnetic field, quadrillions of times stronger than Earth's. While all neutron stars have strong magnetic fields, a magnetar's field is in a league of its own, reaching strengths of up to 10 to the power of 15 Gauss. This extreme magnetism defines them and leads to their unique, high-energy phenomena. It's like a neutron star that went through a cosmic supercharger. One crucial ingredient for magnetar formation lies in the progenitor star, the massive star that eventually explodes. If this star was spinning exceptionally rapidly just before its collapse, this rapid rotation plays a key role. As the star's core collapses, all that angular momentum, or rotational energy, is conserved. Imagine an ice skater pulling their arms in to spin faster. The same principle applies. A rapidly spinning core sets the stage for creating an immense magnetic field. This rapid rotation, combined with the extreme density and conductivity of the newly formed neutron star, creates what scientists call a dynamo effect. Think of it like a natural, cosmic generator. The turbulent, conductive fluid within the neutron star's core moves rapidly through its own magnetic field, amplifying it to unimaginable strengths. This process, similar to how Earth's magnetic field is generated, is supercharged, producing the quadrillions of Gauss fields characteristic of a magnetar. It's believed that magnetars form from progenitor stars specifically in the 10 to 25 solar mass range. Stars lighter than this might form neutron stars but typically won't have the internal dynamics or rapid enough rotation to develop into magnetars. Stars significantly more massive, on the other hand, are more likely to collapse directly into black holes. So, there's a Goldilocks zone of stellar mass that's just right for magnetar formation. It's a precise balance of conditions. The extreme magnetic fields of magnetars aren't just for show. They drive incredibly energetic phenomena. Magnetars frequently emit powerful bursts of X-rays and gamma rays. These bursts are thought to be caused by starquakes, sudden shifts and cracks in the magnetar's incredibly rigid crust, which tear through the tangled magnetic field lines. When these lines snap, they release enormous amounts of energy, detectable across vast cosmic distances. These bursts are some of the most luminous events in the universe. While all magnetars are neutron stars, not all neutron stars are magnetars. Many neutron stars are observed as pulsars, which emit regular, lighthouse-like beams of radio waves. Magnetars, however, are primarily characterized by their extreme magnetic fields and often irregular, high-energy bursts of X-rays and gamma rays. While a pulsar's rotation drives its regularity, a magnetar's activity is driven by the internal stresses of its decaying superstrong magnetic field. They are cousins, but with very different personalities. The incredibly powerful magnetic fields of magnetars don't last forever. Over time, these fields are thought to decay, eventually leading the magnetar to behave more like a normal neutron star. This decay process can still generate energy and cause bursts, but eventually, the extraordinary activity subsides. Their active lifespan as magnetars is typically estimated to be around 10,000 to 100,000 years, relatively short on cosmic timescales. It's a spectacular but ultimately transient phase in a neutron star's life. How do we even know magnetars exist, let alone how they form? We can't see them directly with optical telescopes because they are too small and don't emit much visible light. Instead, astronomers detect them by observing their powerful bursts of X-rays and gamma rays using specialized space telescopes. These telescopes act as our eyes in the high-energy universe, allowing us to pinpoint these extraordinary objects and study their behavior from light years away. It's a testament to human ingenuity and cosmic detective work. Even with our current understanding, magnetars still hold many mysteries. Scientists are continually developing new theories and conducting observations to refine our models of their formation, internal structure, and how their immense magnetic fields behave. The interplay between rotation, magnetic fields, and the dense matter within is incredibly complex. Every new burst observed, every faint signal detected, brings us closer to fully understanding these fascinating powerhouses of the cosmos. The universe always has more to teach us. So, let's quickly recap our journey through magnetar formation. It all starts with a massive, rapidly spinning star. This giant burns through its fuel, eventually forming an iron core that collapses. This collapse triggers a supernova explosion, leaving behind an incredibly dense neutron star. If the conditions are just right, the right mass, and crucial rapid rotation in the progenitor, the neutron star's core acts as a super-efficient dynamo, amplifying its magnetic field to truly mind-boggling levels, creating a magnetar. Magnetars are a testament to the extreme physics at play in our universe, pushing the boundaries of what we thought possible. From the gentle glow of a stellar nursery to the violent fury of a supernova, and finally, to the birth of an object with a magnetic field strong enough to distort atoms, the cosmos truly is more wondrous than we can ever fully imagine. Understanding these incredible objects not only expands our knowledge of the universe but also challenges our understanding of matter itself.